Yeah, down there. There we got it.
All
Okay.
righty then.
Yeah. Uh, it might surprise you to learn, and you chip in anytime you'd like, Mike. If no one had evacuated Fukushima, the maximum downwind dose of radiation would have equaled one CT scan. And that
Right.
will be reviewed further in chapter 1.
Right.
Another thing, the average dose received by anyone downwind from 3 Mile Island was less than that from a chest x-ray.
You
I
know, when
would,
I looked into that, and the highest dose was just slightly more than a chest X-ray. And so it isn't like, well, yeah, that was the average, but then a couple of people got super nailed. They didn't. It
uh,
went from 0.8 millisieverts to 1 millisievert. 1 millisievert is a human chest X-ray.
I wonder how far downwind would go. I was in Westchester County when 3 Mile Island happened. Would southern Westchester County be downwind? I suppose it would be.
Well, I guess so, but the farther down you go, the more dispersed it is. And so,
Sure.
I would think the first couple of miles from the plant. But
Yeah,
in any event, in the area that was examined, it was determined that the average dose was less than a chest X-ray.
yeah, yeah,
So basically, the whole world flipped out about an unscheduled chest X-ray. That was
well,
really 3 Mile Island. No, seriously. I mean,
yeah.
what happened is people flipped out over an unscheduled chest X-ray.
Yeah, it was a
Yeah,
movie, the China Syndrome,
yeah.
that really sparked, and a lot of that I think came later, because at the time, it didn't even, I don't recall it getting in the newspapers, but I imagine it did. Back then, I wasn't reading the newspaper much and getting my news off TV, and I don't
3 Mile
recall.
Island happened, I think. The movie was released, I think about 2 weeks before 3 Mile Island happened,
Yeah,
and that boosted the movie.
yes,
Um, Yeah.
right.
So yeah, it was just a lot of paranoid conflation, and it's nuclear fear. I mean, behold
Mhm.
the power of nuclear fear. The entire country flipped out over an unscheduled chest X-ray, and then all of a sudden we started building more coal plants.
Right.
And a survey that was done after we finished the book determined that there was about 460,000 U.S. mortalities that were hastened from coal in just the first 10 years of the century.
Oh,
And so I mean, you could wildly guess that it could be 3/4 to a million people since 3 Mile Island had their deaths hastened from coal, and 3 Mile Island made nuclear fall out of favor, and it was over an unscheduled chest X-ray.
yeah. And then we had this very interesting statistic. More people die each year
Mhm.
working on wind turbines and rooftop solar than have ever died from American nuclear power. That's a pretty amazing statistic.
Yeah.
Um, Going back just a little bit here, I'm
Mhm.
catching ahead of myself. Um, the false estimate of 4,000 future deaths from Chernobyl was based on a 1927 experiment on fruit flies conducted before low levels of radiation could be accurately measured and delivered. That's discussed in chapter 9. And then,
Yeah, and that's also discussed in the short book I wrote, the L&T report,
right,
which is about Herman Muller's
right.
BS or bad science
Mhm.
on low-level radiation.
Yeah,
Oh, that's in
that's
the next
also
beat.
in chapter 10 also. And
Yeah.
then we have the story from New Jersey High School, where the chip of pottery was left, and he was it was about the size of a quarter, and he zipped it in a baggie so no one would touch it because he had to stay home during a rotating COVID schedule. And someone realized that what was in the baggie, and so in an abundance of caution, the entire school was evacuated, and the hazmat team was called. In less than 30 minutes, they had removed the offending sample and declared the school, cleared the school for reentry. Then they paid a call on the student. The budding young scientist was surprised when he opened his door. He thought it was common knowledge that anyone can buy old Fiesta ware online or in pawn shops or flea markets all across the country. It had been a collector's item since the 70s, when the company stopped using uranium tinted glazes. He even put the chip in a baggie. And so that's how the little chunk of Fiesta ware with a whisper of a faint trace of radiation cleared out an entire high school, even the science teachers, and made the national news. It is nonsense like this that inspires us to write. What a nice beginning. And I had was really doesn't say here, but I heard later that they were thinking of expelling him from school. So
Really?
that was word that I heard. I don't know how true that is, but that came from something I've been reading on the subject. So
It's
yeah,
astonishing. Yeah.
yeah,
Yeah. And it seems to me what happens is that people get so propagandized that they started seeing it in terms of good and evil,
yes, yeah,
and then he's evil. He must be expelled from our
mhm,
ethical, righteous midst,
yes.
that kind of a thing. Yeah.
So this is before we get right into this, is some of your preamble, and
Mm.
I like these pair of slides because it shows right away the ridiculousness of it all. This epicenter was right next to Onagawa. Onagawa wasn't affected at all because they built proper seawall, but the seawall at Fukushima Daiichi was only 4 meters. I think that's representing the seawall, and it should have been 14 meters. And they were
Well,
advised of this, right?
yeah. Well, actually, what it is Onagawa had their generators up on a bluff, and the thing about Fukushima was, regardless of the seawall, that original piece of property was 135 meters above sea level, and they lowered it to 10 meters above. Oh, no, it was 35 meters above sea level, 100 feet, and they lowered it to 10 meters above sea level. They actually lowered the site, and then they could bring in equipment from the sea to build the plant. And then they built a seawall, which is like nuts. And so basically what happened is they brought the reactor down to the level of the sea in a known tsunami zone. In
Yeah.
fact, the country coined the word tsunami.
Okay. Yeah, it's really incredible how those things evolved, and this again followed pretty amazingly. Um, Rumors of the fire prompted the second point here. Greg Jesko, an unusually trained person to head our Nuclear Regulatory Commission, to enlarge the radius of the exclusion zone fourfold, that is from 20 kilometers here to 80 kilometers. He said, this is just for Americans living there. But of course, the Japanese picked up on this and they wanted to do the same thing, largely responsible for the long-term unnecessary dislocation of tens of thousands of people. Many local evacuees were paid money by the government, but they still will not return. And I understand that suicide has also been a factor of fear.
Mostly despondency rather than fear.
Yeah,
It's like, the average background dose in the Fukushima area is 2 millisieverts. They want to lower the radiation level by removing topsoil down to 3 millisieverts, 1 millisievert above background.
mhm,
And so they scraped up that soil is, been cultivated for thousands of years. And they just they've been scraping it all off. And the farmers are committing suicide from despondency.
yes, terrible.
They're
Thank
living
you.
in temporary housing,
Yeah,
they're refugees in their own country, and like I point out in the book, if the farmers just moved to Denver, that Denver has an average background of 7 millisieverts, which is more than twice what their government is trying to get their land back down to.
and that's sad.
It's blatantly, obviously nuts.
Yeah,
It's ridiculous. It really is. And what astonishes me is how people can't just sit down and go, oh, well, this is 2 millisieverts. They want to get down to 3. People in Denver are living at 7. People in Kerala, India have a background radiation of 70. And they've been growing all their own food in that soil. And they have the greatest life expectancy in the country of India.
Yeah, that is fascinating. Well, we're going to be touching on similar statistics along the way, so we'll pick that theme up. What I wanted to show here is more detail on the Earth's core. I use U as a short for uranium, and PB is a short for lead. And we'll get into a couple of others here, TH for thorium and K for potassium, for people who didn't take level 1 chemistry when they were in university or high school. So the point is that the thorium and potassium have been helping to keep the Earth warm, along with the heat of friction of the circulating core itself. And this constant motion of molten metal, mostly iron, produces our planet's magnetic shield, thereby deflecting charged particles in the solar wind. Good planets are hard to find. Mars is not so lucky. I just love some of these statements. And this slide in particular, I like, showing the friendly sun there on the left and showing the Earth over here with its magnetic fields. And of course, the solar flares coming directly toward the sun and bouncing off in the solar wind, glancing higher up because that goes all the time. The solar flares only when the sun is warming up and flaring for some reason which we don't fully understand. Respect is good, but nuclear fear helps only the fossil fuel industry. Very well put. As a retired radiation oncologist, I thought it might be good just to review for people what these various penetration of various zoomies are. We all started with alpha, beta, gamma particles, and you can see them there on the left. The alpha particle can't even go through paper, but they are basically helium nuclei, and they do arise from certain radioactive elements. Californium-252 was used when I was recruiting faculty at the university here to try and see if we could destroy cancer with it, because if you can get the alpha particles, or basically helium nuclei inside a cell, you could do a lot of damage to the cancer cell. But how to do it specifically was very difficult to do. We struggled for quite a while with californium. Today, we've made huge progress since then. We're able to link helium nuclei to very good linking monoclonal antibodies, et cetera, so we can do much more damage 40 years later than we could, specifically to where we wanted to go, than we could 40 years ago. But so it has more relevance today medically. Then the beta rays, which are just electrons, and they can be blocked by metal. We use them on linear accelerators to get different depths and penetrations of electrons, again called beta. Let me jump down for a moment to gamma rays. These are much more penetrating. And the only reason they're called gamma rays is that they were going through the alphabet and they thought, well, the next one is gamma. But gamma rays come from the center of a radioactive nucleus. And so they're generated then from things like radium, for example. And but if the X-rays are made by a machine, as Röntgen did, then they're called X-rays. They're one and the same thing. It's just that X-rays are made by linear accelerators today in cancer treatment, and gamma rays are made by radioactive isotopes. So but they do require a lot more penetrating power depending upon their energy, and of course need lead for proper shaping fields if you want to, or total blocking if you want to. Neutrons, not so much used. Today we're modifying that a little bit by using protons, and that's popular for certain children's tumors, and people are thinking about salivary gland tumors and prostate cancer, and that's still evolving. But neutrons per se, not so much. So that's the penetration zoomies, which I think is good to review, and the history of it. There's another one down here that's good as this one. I like how you put it. We can use nuclear waste to power the cleanup of all other waste. It's only waste if we waste it. And you come up with this EROI, energy returned to society, divided by the energy required to get it. For a fast neutron reactor, it can be 2,000 to 1 here.
Yeah.
But we talk about that a good bit. Also note the buffering, which you see here for solar and wind and solar, concentrated solar. This buffering refers to the backup that's required by energy storage or other power plants, often needed for renewable energy sources. So a very powerful slide there. This one goes into the mining more. I'd really forgotten how much mining is done in Canada and Australia. And those are big sources. But we do mining in various ways. We used to just dig it out, but now over half of it is extracted by in situ leaching with either sodium bicarb or dilute hydrosulfuric acid, depending upon the chemistry of the ore. This avoids some waste rock and dirt tailings, but the fact remains that for every kilogram of uranium-bearing ore dug or leached out of the earth, however way you're getting it, you're only getting 78 thousandths of that, which is about 78 grams on the average kilogram, will be the lighter fissile isotope of uranium oxide. So it's still very inefficient. To their credit, Canada and Australia restore their mining sites completely. In any nuclear Australia, they graze cattle on top and rehabilitate their uranium mines. Easy to do, but the mining footprint of nuclear fuel can be reduced to nearly zero with existing and future Generation 4 technology. This paragraph, I didn't realize, you have it in various places, and as I was building these slides, I keep ending it up with the good news is, and so you'll see in several places the good news. It's interesting that Kazakhstan has so much mining, and I'm not sure whether
it's mostly ISL in Kazakhstan, but nevertheless, about nearly half of the uranium used on this planet is mined in Kazakhstan, and which is and Russia. So Kazakhstan plus Russia is 51%, and that's Kazakhstan's a vassal state of Russia. That's why I'm so gung ho about seawater uranium. It circumvents all of this.
Yes,
all of it.
Yeah, and I think that there's fascinating evidence that seawater might be, and I'd like to know more about that, might be used more efficiently if we work with certain species of kelp or algae. And I'd like to learn more about that as time goes on.
The effluviant from seawater desalination plants is the perfect place to mine seawater uranium, because all the minerals in that effluviant are much higher concentration because a lot of the H2O has been extracted. And so you have a concentration at the tail end of a seawater desalination plant of mineral rich seawater. And so that's the perfect place to mine it.
Where are
Or
those
well,
located?
not mine it, harvest it, excuse me.
Sure. Where are those located today? Are there many of them?
I don't think there's that many of them, but it's a good start. And
Sure.
in my opinion, I mean, there's a little saying I came up with: desalinate or depopulate. We're going to have to start desalinating seawater. We're just going to have to do it, and that provides an opportunity to harvest the uranium out of that effluvium, which is, like I said, a higher concentration than regular seawater.
Sure. Okay. Thank you for that perspective. We also need to be aware of what's left after this whole idea of the spent fuel is where the uranium is 4%, 235. This is what we use very much for energy, and when it gets reduced to 1% or so, then we shut it down and remove it. And when we remove it, we also are removing some fission products, which we'll talk about, as well as some plutonium. And so if you add up the uranium and the plutonium, then you've got almost all of this is reusable material. And the fission products we need to focus on a little bit here. So we'll go into that. Also, I need to talk a little bit about transuranics to make sure that we understand what transuranics are. Here is the periodic table. Here is uranium, Neptunian. I think I have to remember Pu instead of
Plutonium.
platinum up there is the T is RU. So I think of it as something that's smelly, something you don't want to get too close to, Pu. And that way I can remember that it stands for plutonium. But americium is in our smoke detectors. And then we move on from there. So these are basically the transuranics are bigger than plutonium. All right. And so that's what we mean by that definition. What we also have to deal with are the fission products. This is a fascinating table I hadn't seen before. And I guess you put that together, right?
No, we pretty much copied it from, it's basically, it's known data. We just compiled it so it's usable. But basically, there's two areas of the periodic table where fission products are formed.
Yeah. Here's the good news again. Both used fuel and depleted uranium can be recycled and thoroughly efficient in fast neutron reactions. So I keep coming up with the good news. It's fascinating that we tend to have the fission products in two groups. It doesn't split right equally down the middle. There's sort of a gap in here.
Yeah.
And
yeah, exactly. Not quite. It splits, more or less kind of whatever. That's basically what you're looking at there is the split and the range of material that each half, for lack of a better concept, forms.
Yeah.
Yeah.
And then we have this fascinating curve for fission products here that we can't forget, because if we focus on the fission products, if we deal with plutonium and the minor actinides that might be left, and make sure that most of the material gets fissioned, which would only happen in generation 4 type reactors, then you can shorten this time by a couple of logs, and just deal with the fission products. So this is an interesting statement here, and I think true. DU stands for depleted uranium. and that might be accepted by the public over
Spent nuclear fuel.
the nuclear fuel. Thank you. Since depleted uranium is almost pure U-38, 238, and only slightly radioactive, but we have plenty of both, so we can work with those. I think this is a fascinating slide. The top one, it relates more to France, where they reprocess it. Generally, this reprocessing is done in just one more round of slow spectrum light water reactors, and this was often done just once, so it's fairly inefficient. But this one we're going to show in a later slide coming up shortly, reprocessing and recycling, which I think is fascinating.
Yeah.
And then this one, of course, the pyroprocessing and embedding in glass is something that we may need to do for some of the otherwise impossible isotopes to deal with. And if it's there's a lot of plutonium of very close atomic weights, then it's very hard to separate. But,
well, there's one thing I want to jump in and say that the transuranics that come out of fission, there's such a small volume, like the amount of americium per ton of uranium, that winds up to be americium. It's such a small volume that in a molten salt reactor, you can just leave it in the damn reactor. And it'll eventually pick up a neutron and turn into something that'll fission. And even if it doesn't, the transuranics in a molten salt reactor might be the size of a baseball. So you can literally just leave it in there.
Yes.
Yeah.
Okay. Well, this next slide is, where is it coming up here? There. I think, yeah.
No.
Let me try one more.
That's a rerun.
I guess I don't get it there. But anyway, maybe it'll show up later. Chapter 6, Back to the Future. A lot of people don't realize that the experimental breeder reactor, this is the EBR-1. It's a museum. I visited the museum. It's a fascinating place in Idaho, but it ran on spent fuel for 13 years.
30 years.
Well, that's what they say, 30, the first one. Yes, the second one, 30 years. The
Gotcha.
EBR-2, which is not open to the public, that did go 30 years. But the one is, it only went 13, but still, so this refers to the more advanced facility. This is where I say, cut all power to a more advanced facility, meaning EBR-2. And the reactor shut itself down without assistance. Sadly, a poorly designed reactor in Chernobyl melted down only 2 weeks later. So our great success was lost to history and then shut down by Bill Clinton and Al Gore, of all people, in 1994. So people still argue about the rationale for that. Some people say it was that they were making agreements on reducing the amount of warheads in both countries, and so they just didn't need to make any more plutonium. And various other people argue against that.
Yeah, there's also a theory that they did it to curry favor with the anti-nuke hippie crowd for votes.
Right. Yeah, that could have been too. There were probably several reasons for that. This one is really, I think, of the 6 families of Generation 4 reactors, this one I really like because it is liquid fuel, and with molten salt reactor, self-heated by salt, it forms nuclear fuel by a salt form, I'm sorry. It dissolves in the working fuel itself by combining 3 functions, fuel, coolant, and working fluid, in an unpressurized system, and that's key. Unpressurized allows the fuel salt to expand or contract itself as it makes or gives off heat. No electrolysis or pin fabrication is needed. All those costs can be reduced accordingly, and this is sometimes overlooked. There's a frozen plug here with a planned space to absorb material in case power is lost. This frozen plug melts, and this will be stored in vessels where the whole reaction will come to a stop.
Yeah, what it does is it breaks up the fuel mass. You need
Yeah.
a certain amount of fuel in one space to get the party started. So
Yeah.
if you split it into 3 or 4 modules, there's not enough in any one module to make whoopee. So it just kind of sits there and cools itself eventually. You literally pump it back into the reactor and it's all one big happy party again.
Yeah.
So I
That's how
have a
simple it is.
I have a question, if you can hear me. So
Mm.
these pumps that run this whole system and valves, they're really able to handle the caustic environment, right?
Well, regarding the caustic environment, Ed File points out and Stephen Boyd points out that the bugaboo of the caustic, the corrosive environment of the salt in the earlier reactors was that there was impurities in the salt and led to having oxygen and basically water in the system.
Yep.
And it's the water plus the salt that corroded the material. And Ed File had originally said, well, we can just use stable salt in a fast neutron reactor. And he later, Stephen Boyd later got him to see that, no, you can't use table salt because table salt has some moisture in it. And you have to completely get all the hydrogen and oxygen out of the salt. And so the key is a completely no water no water whatsoever at all in the salt.
Right.
Now,
And
this has been shown by
Copenhagen Atomics. Right?
exactly. In fact, they've got quite a business going, just purifying salt. So it's these problems are solvable. But when you read all these essays as to the problems of this by people who don't understand and haven't really looked into it carefully, it makes it sound like it's huge problems with MSRs that haven't been solved, but in fact they have. And
the reason why the MSR at Oak Ridge that was such a mess that cost so much money to clean up is it was simply shut down, and there wasn't money right when it was shut down to properly clean it. And then the corrosion continued apace. And then it's like, oh my God, it's such a mess. We can't do this. Well, if you took care of it in the beginning, it wouldn't have been.
Sure.
But the money wasn't there. And so all these excuses get whipped up into just basically a paranoid propaganda frenzy. And most of it is just BS.
Yeah.
One quick question. The diagram, where is the molten salt in that diagram? It's not, is it in all the yellow areas?
The vertical yellow columns inside the big reactor up top, that's the molten salt. And the molten salt, by the way, is actually kind of green. It's not yellow. And it basically looks like Dawn dish soap, and it flows like Dawn dish soap. It's a little viscous, you follow me? But it's pretty much like watery. And that's where it is.
And it's fluorinated, right? It's fluorinated?
It's a fluoride salt or a chloride salt, depending. Yeah. Okay. So this is probably a fluoride salt reactor here, which is a slow spectrum, whereas a chloride salt is a fast spectrum because the chloride salt doesn't slow neutrons, whereas the fluoride salt slows neutrons, and slow neutrons get along really well with uranium-235.
And they use some beryllium in there too with the lithium.
Great, thank you. Thanks.
Mm-hmm. Yeah.
So then we have this fuel conversion. I think this is incredible.
This is cool. Yeah, I love this.
Chop up the pellets and put them in a zirconium chloride oxidizer, and the zirconium oxide is removed, and now it's ready for fast neutron molten salt reactors. So they just, I think, exchange their oxygen atoms for zirconium. And so there's no isotopic separation. All uranium isotopes remain in the mix at all times. So weapons grade material cannot be isolated.
And the plutonium isotopes, basically all transuranics remain in the mix.
Yeah.
Yeah.
That's a great.
Yeah, so it's jungle juice is what it is, you know.
And who's doing this now? Anybody?
I don't know if anybody's doing it now, but they should be, and it's
Yeah.
pretty straightforward stuff.
Yeah.
If anybody would be doing it, my guess would be INL or Argonne, one of those guys. You know?
Okay.
Yeah.
Right. And this is the point that you make about seawater. Endless supply, 250,000 years of carbon-free fuel. Security to any country that can enrich its own uranium without waiting for Gen 4 technology. And I think that as the costs of some things go up and the simplicity of this improves, this could be more and more important. What I find kind of
what's the cost of a lack of accessibility, geopolitics, imports, tariffs? What if we start like not being friends with Russia? You know, you eliminate all that geopolitical garbage, and you have a 100% domestic energy system.
Yeah. Well, I think it's
Forever.
interesting that thorium does not dissolve in seawater, but uranium does. I think that's a fascinating distinguishing. But fortunately, thorium being so useful as a breeder, you don't need vast amounts of thorium, and so it's not a major problem.
Yeah, no, thorium can be harvested from the tailings at phosphate mines.
Yes.
And then we have a bunch of phosphate mines down in Florida, so we can probably extract a lot of the thorium that we need. But you know, the thing about thorium is you need uranium to get the party started.
Yeah.
Because thorium is not a self-starter.
That's right. Yeah. Well, we better do it before Florida goes underwater.
Yeah.
So, to be perfectly blunt, I like that one. And this is showing how renewables are so dependent upon biomass. 39%. Really pretty sad that we some of it's waste, but some of it's wood. And in Germany, they want to make sure they make their quota, and so they import wood from Canada and Brazil and the United States, these wood pellets, and burn that, so they'll have all this renewable energy. It's almost as bad as burning coal, not quite, but really, and the big point about this slide is most media reports cite installed capacity rather than capacity factor. The former, the installed capacity, relates to the peak performance under ideal conditions. And I'll have some data on that from my own solar panels in a couple of weeks and show you actually how crucial that is and how rarely we keep talking about this peak performance. That's how it's bought, that's how it's sold, but it's really understanding the amount of, when it's giving energy, that it's you're beginning to see the real world, or in this case, the American averages of actual energy consumption. And so I think that's a really important slide.
Yeah, the thing, you know, basically what we point out in Roadmap to Nowhere is we call it truthiness in advertising. That they are just hype. They're using the installed capacity numbers because they're 2 to 4 times higher than actual performance numbers.
Yeah. Yeah.
And so they're running around going, woohoo, we installed all this stuff. Yeah, and it's snowy and cloudy, and it ain't gonna do shit.
Well, not only that,
what does it do? Not what did you put in the ground.
not only that, but it's I called some of these people
What'd you
uh,
call them?
to I think the people who recycle. Um, excuse me. Um, the solar panels and this business here, 12% solar. That of course is 2019, and we're 5 years beyond that, but I don't think it's changed that much since 2019, reasonably current data. So I called the people. There's a place where you can send your solar panels. They said they'd happily take them. I didn't get around to asking how much, but they do it in one place in the country. It's in Maryland, and I asked them, well, what do they do with it? Well, they take off the glass, of course, take off the aluminum frames, and they slide out these sheets of
Solar
photovoltaic
cells.
material. Yeah, and they slide them out, and what do? They put them on a grinder, and the ground stuff goes into cement, so that in the future our cement will be laced with photovoltaic chemicals.
We'll be
Photovoltaic.
walking on sunshine.
There you go.
Richard, could I ask a question?
Sure.
I'm curious about the petroleum here. Is this used for making electricity or is this for gasoline? What is this energy source being used for?
Well, I would say that a lot of it is islands. There are a good number of islands, Hawaii, for example, but many others, where they don't have natural gas plants, they don't have coal. And so this is shipped in daily for all of their energy. There's a friend of mine who's very keen on selling solar panels in Hawaii, and I guess he's making some progress, but there's still, and of course, that's not a big improvement, as we just are saying. So petroleum is largely used that way. Also, some people just don't have the facilities for natural gas, and so they just use in the broad field petroleum, which could be a type of crude oil, like some sort of propane, for example, might be used where you can't easily get natural gas. So it's used.
Isn't this slide primary energy, not electricity? I believe it's primary energy, and then that would be transport for the petroleum.
Okay,
And the
that's
yeah.
okay. Okay, thank you.
Yeah, I forgot about that. That's a good point.
Yeah.
Okay.
Transportation really.
Transportation is a tough nut to crack. It really is. You know, I mean, it's just liquid petroleum fuel is so damn convenient.
Yes.
I mean, it's really a marvelous product, except for all the waste. But it's a marvelous product, you know. And it's like, how do you beat that? It's tough.
It's energy dense.
The military have been beating it for years. Their aircraft carriers are powered with nuclear energy, and you know, we should have been doing that long ago with our fleet of ships.
Yeah.
But it's energy dense, like you can't believe it, and it stores energy without losing it.
Yeah,
it's remarkable.
But it's a more remarkable product. Unfortunately, there's a downside.
Yeah. And it's hard to get it out of airplanes too.
My question was, I was just trying to, almost everything else is used for generating electricity.
You're right.
And so I was just a little curious as to whether the petroleum was being used for that or whether it was our usual thought of for transportation. So
it's probably also home heating oil for houses too.
Yes.
You know,
okay.
Petroleum.
Yeah. Very good. Okay, so Jim Hansen has written, the notion that renewable energy and batteries alone will provide all needed energy he uses the word fantastical. Worse, he says, tricking the public into accepting the fantasy of 100% renewables means that in reality, fossil fuels reign and climate change grows. Now, I went to a meeting in Milwaukee 10 years ago where James Hansen was speaking, and it was the audience was cut down. They had a sub audience, and he came into this panel and clearly knew what he was talking about more than anybody else on the panel. And they were very careful to restrict the noise, and they recorded it. And when it came to the part in the panel where James Henson made this sort of remark and pointed out to people that the new advanced reactors would be able to consume virtually all of the fuel rather than just 2 or 3%. The audience just gave a gasp of realization, and
Wow.
that was 10 years ago.
Yeah.
We're still a long way from that Milwaukee surge of information. So
Yeah.
then he does deal with hydrogen in an interesting way. He says hydrogen fuel is something we humans have to make ourselves. We have to expend energy to separate the hydrogen and the oxygen that formed the water molecule in the first place before we can use the liberated hydrogen as fuel. And when we do this, we only get back a small portion of the energy expended in the process. The nice thing about actual fuel, whether it's wood, coal, gas, or uranium, is that the first step of putting energy into it has already been done. All we have to do is release the energy in the fuel, and then he says, responsibly, please, because uranium fission reactors run on such energy-dense fuels. They would be far more practical than renewables for powering a hydrogen infrastructure, and we've actually gone so far as to giving it a name. I think they call it pink hydrogen or something like that.
Yeah,
Did it-
whatever. Yeah, all those color stuff, right? Is that our rainbow hydrogen? So
Yeah.
yeah, we go into this in detail in Roadmap to Nowhere, because Jacobson has this idea about making all this hydrogen, and so we just replicate his grid with nuclear reactors and go, well, we can do it for this, you know.
Yeah. And then the wind power leaves waste too. Nuclear is the only production system that accounts for every speck of its waste. Here you can see a plow plowing under these are cut into quarters or less. So we see them in quarters when they go down the highway. These may be shorter cuts, but these landfills for wind and solar waste are expected in the coming years. People talk about how long these blades will last. They're said to last about 25 years over land, less than that considerably over offshore. And they're difficult and expensive to remove offshore. So, but here they are in Casper, Wyoming, all chopped up, and there are going to be a lot more of them until they're not really telling us very much about the abandoned farms that we have yet to deal with. It's not, you have to dig hard to find out how many birds are killed by them, and many of them are going defunct in various places. So what we really need to understand is comparative death print, where nuclear has such a low death print, it's 24 times safer than photovoltaic, 178 times safer than onshore wind, 800 times safer than offshore, and so on, and 12,000 times safer than coal.
And the safety of wind and solar has to do with a lot of it are people falling off roofs, installing rooftop solar, and then injuries or deaths that result from working on turbines. And so it's the installation and maintenance is a hazardous activity. And that's where the deaths, those are the deaths that result.
Yes, that's right. And when I talk to politicians, particularly in a green city like Madison, about this, they say, well, nuclear just is too dangerous. And I have a really hard time getting through because this is just deeply into the psyche of people in green Madison.
Nuclear fear.
Yeah. So why are some people still anti-nuclear? I really like this first sentence. The I thought this was worded beautifully. The information age of the 20th century has brought us to the disinformation age of the 21st century. Through the magic of the internet, the crazies have found each other. Now it's all too easy to get lost in the weeds. The authors, you, Mike, and Tim, freely admit that you're nuclear advocates, but I think you do cite legitimate sources for much of what you write.
We have over 500 links in the endnotes.
Good. Yes, you do have a lot. So the nuclear power is the safest form of mass energy production available, providing one of the lowest life cycle CO2 emissions of any energy source. And it's, but I really enjoyed in that chapter 8, this line. It says so much about what's happened in the second decade of this century. This is a catchy image. The
thank you.
MVP model.
I made that one up myself.
Yeah, that is cute. Swag for scientific wild ass. Yes, yeah. Right.
Oh, that's something that Stephen Boyd gave me, but I made the graph myself. Yeah.
That's good. Yeah. He made two false assertions, Miller. No safe dose of radiation, and all doses are cumulative. I mean, this is so it runs against the whole concept of radiotherapy that was shown at the Curie Institute and other centers in France. The pioneers of radiation is that radiation therapy for cancer is that there are safe doses of radiation, and that they accumulate to some degree, but fortunately there's a lot of recovery, and we'll show some slides to that later. So Miller's model is still regarded by many as a proven theory, even though it's so badly flawed. And it increases the cost of both medical and energy-related radiation facilities. When I talk to my colleagues in radiation, and those who even teach radiobiology, they say, Richard, just give up. It's never going to change. And but we have to keep informing people. With a misinformed populace in the midst of an escalating Cold War, Hollywood, and this was some time ago, we're talking in the atomic bomb testing.
Mid-50s,
yeah. And this is, did somebody make up this, or was this actually from a comic book?
No, I had the concept, and we had an artist draw it, and then he's English, and he had all these English aspects in here, and I Americanized it. So basically, I was like the art director, make the banana green and put the 56 Chevy Bel Air station wagon outside. And he originally had porridge in the bowls, and I'm like, they don't eat porridge, they eat cereal, that kind of a thing. But anyway, no, it was my idea. And I had it rendered by an artist. So
that's clever.
Thank you. Cute? I love it.
Yeah. Fascinating. Okay, let's see. How am I gonna? There we are. Now we're going to continue this on November the 4th with more detail. But I thought that we could. We're just an hour and 5 minutes, and we tend to like to load up the questions. So we're open for questions at this point.
Don't be shy.
Yeah,
go ahead.
I've got one question of earlier, the EROI under that slide.
EROI.
EROI. Or was it right before that? I don't know. Neutrons and protons. And Richard, you were talking about protons used to treat prostate and other cancer, proton therapy. One of them more powerful at destroying cancer than the other? I mean, protons they're charged, so you can direct them a little better, can't you?
Yes, they're not used in in many facilities, I think there are 2 or 3 facilities, maybe in the Midwest and a few on the East Coast and West Coast. But they were originally thought to be useful, mostly protons for children, where you want to have a fairly rapid burst of energy in a localized volume. And in salivary gland tumors tend to be fairly resistant that if they come back after surgery, they can be fairly resistant to conventional radiation. So salivary gland tumors became useful, and now people are arguing that they can be more effective for prostate cancer. But prostate cancer has so many different avenues and ways to treat that
Yeah.
It's going to be hard to prove that one. But
I
it's
see.
yeah.
About
Yeah.
the same energy level, the neutron and the proton, as used therapeutically. I don't know if the neutrons are even used therapeutically. You they're not charged, so you can't really aim them, can you?
That's
Yeah,
right.
or focus them. Yeah.
The neutron is used more like an isotope than beam, and so it's really hard to compare. But the energies are quite different. What's really important to get across, I think, in this one is that alpha, beta, gamma idea that started 100 years ago, and in the different ways that they are shielded and used, and how the names have been changed, beta to electrons and gamma. There are even some isotopes that emit very mild X-rays, certain isotopes of iodine, and very useful clinically. But typically we refer to gammas as coming from a radioactive nucleus, as opposed to X-rays that come from an irritated outer shell of an atom like copper in an X-ray tube. So it just, all these names have been used in various ways over the years, but this was kind of interesting historically, knowing the different penetrations, knowing the history, alpha, beta, gamma, and so on, that I thought this was a very nice slide that put together that shows us the history and the differential.
Richard, I have a question for you. Could you talk a little bit about the effect of ionizing radiation on cancer formation with respect to single versus double strand breaks in DNA, and in terms of the difficulty of repairing the damage? Is there let me start. Is there a difference in repairing the damage due to a single break or a double break?
Yes, that's going to be discussed next time, if we can hold that question. But to answer, because that's really a good one. But basically, just repeat the question again.
Well, I was curious about, so a lot of the portion of this book has to do with repair, a biological damage, that the body has a natural repair mechanism. But I wanted to dig deeper into that as to the difference between single strand breaks and double strand breaks in DNA ionizing radiation. And in particular, what I was interested in was the difference between the damage caused by alpha particles versus, say, beta particles, in terms of what would it be true that alpha particles would be more responsible for double side breaks in DNA than beta particles or gamma, for example? That's sort of where I'm getting at.
Good points. Again, the next week is going to be really the way to go, because it goes into this in much more detail. But there are single strand breaks being made all the time in our bodies, and they're being repaired all the time.
Right.
And this is just part of natural evolution. We there's some evidence that evolution requires a certain amount of repair of the DNA from all kinds of things that have been in our environment, which was, by the way, much more radioactive in the past than now. And so repair is going on all the time of single strand breaks. And you're right that if a double strand breaks, that's more serious. But again, it depends very much in the DNA where it occurs, and the length of the strand and what particular material is damaged. So even double strand breaks are being repaired all the time, just not with quite the fury that single strand breaks are, but
Yeah.
both of them are being repaired all the time.
Didn't Jack Devaney go into that pretty thoroughly or some degree? He had a video or slide set, which I recall. Part of the problem is our mitochondria create a lot of things that cause breaks. So any eukaryotic organism has to have a system to repair because of the mitochondria. That was one of his points from early, that he made. I don't know if you guys follow that, but yeah, the double-stranded really take a long, and if you get too many back to back, you don't repair it. It doesn't repair.
Right,
But
right.
you're right, Richard. Where all this happens, there's so many variables in the nucleus as to all of this stuff, and the energies of the radiation. There's just a lot of research that needs to go on, figure all this out more precisely.
Yeah,
So
so I think this goes to the point.
There's been a lot of empirical observation that, in the absence of high doses, the body, if we didn't repair ourselves, we wouldn't exist. We evolved in a more radioactive environment than we're living in now. It is built into the organism. So
Yeah, but the point, I think, is that the body repairs itself until it doesn't.
well, okay.
And that's the
Yeah.
point. And when it doesn't repair itself, and I'm looking to Richard actually to clarify this issue, which is that more than likely it's the double strand breaks that presumably are more problematic for the body to repair itself, because it's hard to reconnect the DNA when you have a double side break, and which leads to, if you look at this chart here, for example, it's the alpha particles that are more responsible. And I'm asking this as a question: are the alpha particles more responsible with double side breaks than, say, gamma radiation? Is that a true statement? And I'm asking that because what we know is that the alpha radiation is deposits all of its energies in such a minute area. So basically, I think it's on the order of 70 microns. So outside the body, alpha radiation is harmless, completely harmless, because it never penetrates your skin. But if you get it into your lungs, then alpha particles cause an enormous amount of devastation, because all the energy from the alpha particle is deposited within 70 microns, and more than likely can lead to a double side break, which then could possibly lead to a cancer. Would you comment on that, Richard, and just say if anything I said there is not true?
No, I think you said everything is quite true. I'm sorry to be a little bit of a niggardly responder on this question, because it's so nicely dealt with in the next talk on November the 4th.
Okay.
He really goes into this in great detail there, and I hate to not just only give it away, but it's done so nicely there that I really hope you will come back on November the 4th and we can pursue it at proper depth. But in general, yes, their single strand breaks are made much oftener. They're easy to make, being it's a double stranded molecule, and for its integrity. And so single strand brakes are made and repaired easily, commonly, and double stranded brakes are more serious. So in your comments about alpha particles in the lungs are true. Also, people are beginning to recognize that not only alpha particles, but simple um, uh, carbon particles have been causing enormous lung damage. These particles that are, I think, 0.25 microns or less, tend to get into pulmonary pathways and cause enormous damage to the interior of the lungs. And we've been suffering from coal-related pulmonary damage for years, and it's only now we're realizing this, that parts of Europe, for example, were very slow to get rid of coal. In Poland was one of the worst countries. They use a lot of lignite, and that's the worst type of coal and really highly polluting. And fortunately, some people with some sense in Poland decided to start building some nuclear plants there and shutting down their lignite coal plants. But in Germany, they have not done that. They've done the opposite. And another slide that we'll be touching on in the next series is comparing France and Germany. And it amazes me that the Green Party in France has so much sway over the public and over the politicians, so they're still cutting down forests. I have two friends in Germany, one of whom owns a forest there, and he says it's terrible to see these forests being cut down for coal and digging up the coal still to this day, when we know better and should have known better for a long time to stop them.
Just one addition, diesel exhaust has a lot of particulates too.
Yes, that's
And that's
true.
what, and the high temperatures that create the NOx fumes, which aren't good for the lungs either, but the diesel, and for a while, the Department of Energy was pushing diesels a little bit, and then they realized that this is just futile.
The diesel in the shipping industry is a dreadful thing, and if we can find ways of more conveniently, and I have some slides again next time on November 4th to suggest that there are companies now where they're in Norway, where they're trying to already plan shipping containers with reactors in the hulls. So this is probably going to be happening in the next few decades outside of the military. For years, military have been using this for convenience. They don't like to have to fuel up in bad ports, so they carry their own fuel with them as a reactor or two. But it's about time that we started to do this with these vast shipping containers, and I think it will happen. It's going to happen a lot sooner in shipping than it is in the air. Having personally fooled around with electric airplanes for quite a while, that's a much more difficult thing to solve. But they both need solving, both shipping.
Have you tried hydrogen?
Not personally, no, but I think hydrogen, it has been discussed here, and that was, I think, discussed pretty well.
Yeah, there's a lot of issues with hydrogen, and it's hard to store, it's hard to do this and that.
Oh
and
yeah. It was a joke.
Yeah, right.
I mean, quite frankly, I think that air transportation is going to be carbon neutral synthetic fuel at the most, and
well, if you can at least get the lead out, that will help. There's still lead going into aviation fuel.
Oh God.
Yeah.
We
need to get it out of shotguns too. They're, instead of using steel shot, they're still putting lead in some hunters' shells because the hunters like the idea of the momentum of lead over steel. So we've got a ways to go to improve our environment.
Yeah. Yeah, at least they're not using depleted uranium,
Right.
which is just a fantastically stupid thing to use for a weapon. So,
Yeah.
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 Can I ask a bunch of questions to Mike, if you don't mind?
Sure.
Great.
Yeah.
So there are a couple things so first of all, I really enjoyed your book. It was very illuminating and provocative, and I learned a lot from it, and I really appreciated all the references. And I wound up actually digging through a lot of your references and reading the reference material. And
Hmm.
so let me just, there were some, and especially, let's put it this way, I really enjoyed the fission part of it. I learned a lot actually about fission from the descriptions in this book. The thing that bugs me a little bit about this book is the part about radioactivity. And if you don't mind, I really appreciate your being in this group and showing up, participating in this. But there were a number of things that I just wanted to clarify. For example, if you don't mind. So
Sure.
so one of the things you show, like I think it's on page 20, you show this graph from Bernard Cohn on basically decreasing deaths per 100,000 as a function of increasing radon exposure.
Hmm. Hmm.
Right. So if you look at the scale, okay, this scale basically it's a little obscured in this picture, but the units here are actually just picocuries per liter. And so to give you some idea, basically the number 4 here is 4 picocuries per liter, which is basically what the EPA says. Above this level, you should be you should be improving the ventilation in your house or stopping up cracks and so on, right? So this is basically background radiation already on this level, not that far from background radiation. Okay, but on page 12, for example, you have a quote from the Health Physics Society, and I'll read the quote. It says, below levels of about 100 millisieverts, greater than background from all sources combined, the observed radiation effects in people are not statistically different from 0.
Hmm.
So my question is, why is it that if radiation, whenever you encounter radiation being bad, you invoke this 100 millisievert level from the Health Physics Society, but when radiation is good for you, like in this picture from Bernard Cohn, you don't invoke this anymore. So this is just background radiation, and we're told here from the Health Physics Society that you can't distinguish health risks that are not statistics, that you don't have good statistics. The signal to noise, basically what it boils down to is the signal to noise ratio
Hmm.
at background radiation is insignificant, that you can't decide anything. So why can you decide something when it's background radiation here, that radiation is good for you?
I apologize, but I don't quite get your question.
Okay,
Could you rephrase it?
I'll try it again. So you remember your Health Physics Society quote, right?
Hmm.
Okay, so when anything's above that, you cannot make conclusions when radiation's on the order of background. That's what it says, right? So why can you make a conclusion? This is also around background radiation for the figure on page 20. Why can you make a conclusion that radiation is good for you in this graph by Bernard Cohn? Am I making myself clear or not?
I think you're making yourself clear, but I don't quite get the.
Okay, well, if you want, we can go on from there.
Sure.
Okay. So that's one of my points is that,
Mhm.
okay. And the second thing that's not made clear in the book is actually what this graph is, which is that I went and I actually read the paper by Bernard Cohn. As inspired from your book. Quite frankly, that's what I found so stimulating from your book is you had all these provocative statements, and I actually went and read a lot of the references. So I read the paper by Bernard Cohn. And to tell you the truth, in your vernacular, I would say his paper is BS, bad science, in your vernacular. And the reason why is this is what's called an ecological study. So what he did basically was, you think about how would you do this basically, right? And you're looking for the impact of radon in your home. So what do? You go into the home, you measure what the radon levels are, and you say, okay, how long have you lived here? Have you had cancer? Right? And you do this for a number of homes and you put it together, and that's what basically the epidemiological approach is. What Cohn did is what's called the ecological approach. So what he did was he took data from each county, the averages of each county, for what the average radon levels were in each county, what the average lung cancer rates were for each county. And then you can see in this, what you have in your book, he says corrected for smoking. When he corrects it for smoking, this isn't even county data for smoking. This is state data for smoking. So this is what's called an ecological study. And there's so-called ecological fallacy, which is that you can't ascribe traits of an individual based on traits of the group. That's what's called the ecological fallacy. And I'm wondering why that ecological fallacy doesn't apply here. This isn't an epidemiological study. So that's my second point about this. First is that this is radiation at the background level, which is really hard. I would grant, actually, I think that's a true statement from the Health Physics Society. So how can we make any claim at all having to do with very poor statistics? And then secondly, there's an ecological study. And I have a third point after that, if you want to comment on.
Well, probably the best way of answering this is to wrap my mind around this is he took the data that was available and made a projection and as best he could, and there didn't seem to be any indication of an uptick in cancer rates with these higher levels.
Based on data in the average for the county. This is not
Okay.
an epidemiological study. He didn't go into people's homes. So for example, I mean, I was just looking at this just the other day, for example, if you take a place like Monona, for example. So Monona is a place not too far away from Madison. So you look at Monona, so you look at the average radon levels in Monona, they're like 3 picocuries per liter below the level. But yet the maximum level in that house is like on the order of 150 picocuries per liter. You don't get data of the maximum levels of, where radiation could be harmful from just looking at county average data. That's my point.
So the data didn't have a deep enough focus to make a determination, is what you're saying?
That's my saying. And there's a third point that goes even beyond that. Well, one more level to this, which is that you can get the same. So let me just summarize this for everybody else too, so I don't lose everybody in this whole thinking. But the claim is, from alpha, so basically radon itself, as we know, is perfectly harmless, right? It's not the radon that's the problem. And the reason is because radon is a noble gas. You breathe it in, you breathe it out, and it never sticks to anything in your lungs. It's what's called the radon progeny, which is polonium, 214, 218. That's dangerous. So the polonium basically can easily ionize and stick into your lungs. And that undergoes alpha particle decay, and it deposits its energies within the 70 micron levels. And so that's really dangerous in terms of lung cancer. All right. So the claim of hormesis, for example, from this plot that radiation is good for you, basically it's saying basically like, okay, that you have this alpha particle emission, and somehow it's stimulating the tissue in your lungs to be more and more immune to, say, other radiation and so on. That's basically what the statement is. All right. So that's just in your lungs. And that's a distinction between radon and smoking. Smoking, I'm sure, as Richard could probably tell us so much more and way beyond anything that I even know about, has all sorts of a phenomenal array of physical problems associated with smoking. Radon is just one, lung cancer, and that's it, lung cancer. So there's a study that was done that you can get this exact same curve if you did oral cancer. And so the question is, so oral cancer. So if you get the same curve from oral cancer, it means it's not from radon. And most
Well, some radon progeny.
right. It's not from radon progeny.
And the radon is measurable, and so they extrapolate from there. Am I
Right,
correct?
but you don't have radon progeny in your mouth or in your esophagus. All the radon progeny is in your lungs. That's the key. But you can get the same curve from oral cancer or esophageal cancer. And so what that says is it's nearly not the radon progeny that's causing this chart. It's really the smoking. That this graph has been really discredited by the literature over and over again, showing that this graph is really showing you what happens with smoking issues when you do the studies on a county-to-county basis.
David McQuaig got into an extended discussion of this online, and I think we should look at what that debate came up with. As I recall, I take your point, but I don't have an answer for you. But I think David McQuaig floated the topic of our discussion, and it didn't seem to, at least to his mind, it wasn't debunked, and the people that contend that it weren't able to back up their contentions. So I'll grant you that there's been a controversy about this, but we might want to look at that, and it might need a correction in the book.
Yeah. Let me just say that there's an excellent, so basically I'm quoting the peer-reviewed literature, as you were yourself. So there's an excellent paper by a guy named Puskin, who basically did all this and looked at the county data for different types of cancers and correlated it with the radon, just like Cohen did. And basically I'm quoting his result, that you get the same graph from oral cancer, esophageal cancer, and then things that are more removed from smoking, like prostate cancer, breast cancer, and so on. Actually, there's very little correlation here. And basically, if you dig down into this is really smoking. This chart, not radon.
Well, that's very interesting. If you could send me
Sure, I'd be happy to send you this. I think it's a great discussion. I mean, I think let's put it this way. I knew none of this before I read your book. So what I'm really thankful to you is there's so many things that I learned reading this book that I hadn't known before. And so I started looking at this. So there's a lot of things. And I don't want to take up I have a lot of other questions too, and maybe, I don't know, we could do this, through email or whatever, but if other people have questions or comments too, if there's more time, I have other questions as well.
Yeah, well, thanks a lot. Because if I was led astray by this and didn't get it right, then when we do a revised edition, I could take a look at this and see what I can do to make
Yeah.
it more accurate.
Yeah, so I don't know if somebody else wants to jump in, please feel free to do and shut me up, but there are a lot of interesting things that I saw in your book, and let me pick out another one.
Sure.
Um,
So please just cut me off if you want, but
Can I just say one thing? Ty,
Okay.
you made this point of hormesis and how the body may actually respond positively to radiation. And that, the liver does that with toxicology. There are many chemicals that trigger the liver to jump in metabolically. And, this is such a complicated issue. I don't know how you can tease it apart with just a few graphs, but hormesis, these endonucleases, that they could be triggered too with certain levels of radiation and then go above and beyond their normal level. So this is a whole complicated thing. That's all my point.
I have a little comment to make that doesn't elaborate too much on answering the question, but might be of interest to the group. I spent a summer at the Curie Institute in Paris, near the end of my residency training from New York. And the Curie, they're so busy treating cancers because the surgeons are not very aggressive there. So the surgeons kind of operate at the beck and call of the radiation oncologist. And so they're very busy treating cancers and don't do a lot of time on causing the cancer. But when I was there, I did do some analysis, and I found this interesting thing that the French like to taste wine with little pockets of taste buds that are on either side of the epiglottis, sometimes referred to as the piriform sinus. And they just love the flavor of a wine there. And when they sip a glass of wine, they just savor it. They don't swallow it. They let this wine just sort of nestle there next to the epiglottis. And then they'll take, of course, a puff of smoke if they're smoking as well. And what they ended up finding was that when they went back to the causal factors and then the incidence, the risk of cancer was a particular level with smoking or drinking. But if you did both, it went up sixfold. So instead of just doubling, there was a synergy. And of course, this was basically repeated here by the Millers, who got a Nobel Prize, is showing that the cancer etiology is synergistic between initiators and promoters, things that initiate cancer, such as a chemical, and things that promote it, such as well, in the case of alcohol, it would be a promoting factor. So, in any case, it's clear that the oncogenesis is a two-step process, at least, and some people would argue 23 or more, 20 or more. But so it's hard to sort these things out. But it's I think Mike is we really need to get into the nitty-gritty next time, and I hope that you'll all come here on the 4th, so we can go into a very well prepared session there on frequency of DNA repair and that sort of thing.
Great.
it's now about 20 to 12. We're okay, but do we have any other questions that we need to deal with? Now, I would also suggest that in the areas around Madison, it's known to be where we live here in the lower central Wisconsin, there's quite a bit of glacial till that has been moved around and formed into drumlins as the glaciers melted. In this area, the Capitol State Building is sitting on an ancient geologic drumlin. And so people, when they buy houses here, whether it's Monona or Madison, they are always advised by real estate agents to set up a little tester thing in the basement and see how much radon is there. And if it is, to make sure that that there's a way of ventilating the basement and making sure that there's no smoking in the house and the children are not exposed. So this sorts of things with radon, well, it's important. It involves a certain amount of personal responsibility that is not necessarily showing up in the statistics that Mike is giving us. And I think that for all the interest in radon, part of the interest is also in the things that we are not naturally occurring, particularly the medical involvement that we now take for granted. We talk about everybody getting CTs and everybody getting chest x-rays at various times in their lives. It's part of our medical care. And I think we need to keep all of these things in perspective and recognize that radon, for its concern, is now becoming more and more of a personal responsibility, particularly if you live in the near glacial end moraine. So just a few comments there.
Yeah, what I'm getting from you is that the smoking plus radon could very well be a synergistic issue, but in the absence of smoking, that graph seems to, well, the graph was corrected for smoking. So in the absence of smoking, their synergism isn't there, and that might result in the lower cancer incidence.
Yeah, I think so. As long as we're assured that the smoking was eliminated.
It was actually corrected. In other words, if people were being honest, oh no, I don't smoke anymore, kind of a thing.
Except that in this graph, he doesn't deal with individuals. The smoking data is average state smoking data. That's the thing. It's not on the level of individuals.
Well, okay.
That's what really alarms me, actually, is how far removed from the individuals the Bernard Cohen's data is on smoking. It's state data. Can you imagine that? I mean, average for a state tells you nothing how the individual smokes or doesn't smoke. If you don't mind, can I ask you another question before we run out of time? Just because it's really, it kind of bugged me a little bit. So on page 51.
Page 1?
Page 51.
51.
Yeah, and this, because this is really an important part of U.S. history, which is, you say there was a substantial number of cancers and mortalities in the early days of U.S. uranium mining and milling, most of which took place in the Navajo Nation with local labor, which is really a catastrophe in U.S. history as to what happened to the Navajo during the early days of, when they were trying to mine uranium and build up armaments and so on.
Mm-hmm.
Your next sentence says, at the time, cigarette smoking was common and safety regulations were either lax or non-existent. And I think what bugs me about the second sentence is the order in which you put things, which is, so you call out cigarette smoking in this case. Now, and as we all know, cigarette smoking is an enormous confounder in terms of the effects of radiation on lungs. But here's the thing. The Navajo didn't smoke. And so
thank you for that.
Thank
you for that.
And it's all throughout the literature. I can send you multiple papers on this. This has been enormously studied.
Uh-huh.
That's why the Navajo, it's such a clear-cut case that because if you look at the statistics, and again, this is from the peer-reviewed literature,
Right.
60% of the Navajo never smoked at all. I'm sorry, 60% of the uranium miners never smoked at all. Another 30% smoked lightly.
Yeah, so that will
Well,
taking the confounding out of there, then it comes
It's
down to the
completely
ambient
taken,
dust in the mine.
it's completely taken the confounding influences of smoking out of there. It's
Thank
not
you.
just, and it's not even just true about the Navajo. The interesting thing is, it's true for all the Southwestern Indians at the time. Smoking, they rarely smoked at all. And so that's the thing that bugs me about this is that Navajo is such a clear-cut case, right? And they sort of like, I think it was 1990, they received reparations basically, right? For the fact that
Sure.
the federal government told them, go mine this uranium, but they didn't institute any safety regulations at all. So, that's a, thing that, really sort of stood out for me.
Well, no, yeah, but well, I can see that because it implies that, well, it was just because of the smoking. And what I intended, and probably, well, throwing the smoking in there was a bad idea.
Yeah,
You
I
know,
agree.
that metal mines, in the absence of proper ventilation and respirators, you're gonna have problems. And when those safety measures were taken, the cancer incident dropped at metal mines, not just uranium mines.
That's
But the
right.
smoking, why bring up the smoking? It confounds the issue.
Exactly. Especially,
Thank you very much for that. That's a very good point.
especially for Navajo. And I can show
Yeah.
you, I mean, there must have been half a dozen peer-reviewed papers on this subject that I sort of scanned through some of them, but it was such a clear-cut case. And then let me just bring one more thing, and
Sure.
I'll be done so on page 19, for example, you talk about this whole thing too, which is that in underground mines, radon could be higher than average. That poses a risk, it should be mitigated, but just like mitigation of any kind, the question is to what degree? And I guess the question, that I have, you're asking to what degree, but if you think about this, I mean, have you ever seen a case where there was too much ventilation in a uranium mine? Right? I mean, to what
Well, if
degree?
you ventilate it too much, all the uranium blows away. So you got to watch that.
Well, but you're talking about, basically a cost benefit, and I don't know of any case where we need to turn our ventilation down because we're just costing too much money or something like that. It just kind of, it was a severe problem throughout the 50s and 60s in every country that mined uranium. It was true in Canada, it was true in Australia, it was true in the United States. And what you see, the good news from
We're
this,
very elderly and we don't want to get involved. We've already voted. Bye-bye.
the good news from all this was that, roughly around the 70s or so, when it became clear that mines had to be ventilated, then the cancer rate just plummeted. And you see that very nicely in some of the Canada studies, like the Ontario miner study, for example. You see that. I just have one more thing, and then I'll be done.
Oh, okay. Well, that was a very good point. Thank you.
I think no, and
It's an unnecessary confounding. Yeah.
I really appreciate because it was such a stimulating book. I have to say that's why I just dug deeper and deeper into this because I found it so stimulating. Which is, for the most part, I don't. Most books I read don't do that. But
Wow.
so this is the point I guess I'm trying to make is you have a number of caveats about the dangers of radiation. So you throw in like how much ventilation, or the caveat about smoking and so on. But then on 152, you say low dose radiation hotspots have long been known for their therapeutic effects, such as the radon baths in Claymore, Oklahoma. So I look at that as like, have long been known. I mean, that's, and your reference isn't to actually to the benefit. That's the thing that could have been referenced. I mean, I have no concept that radon baths have health benefits, right? So basically, you're making the statement that their health benefits are radon baths, but it's not referenced at all. So
Okay, all right. Wasn't there someplace else in the book where I talk about the radon baths in Germany that have been favored for like 800 years over
yeah,
the
but that
other?
doesn't necessarily mean, I mean, they put radium in toothpaste or hair tonics, right, back in the day. Those doesn't mean that these are healthy or that this is a wise thing to do, right? I don't know any sane person that would want to sit in a radon bath. I certainly wouldn't. But anyway,
Okay.
I think anyway, I think there's again, I think, this is really interesting. I have a lot of questions too about the Cutler and Welsh paper. I read that based on, inspired by your book. I read that Cutler and Welsh paper, and I have to say that it's a kind of a strange paper. And unfortunately, I guess you didn't get to it, Richard, in this talk. I guess maybe I misunderstood how many chapters you were going to cover. I thought you were going to do 11 this time too, but it's
Yeah.
just, if you look at that paper, it deals with again, this issue of hormesis. And what I find strange about this paper is, I don't know, do you know what happened to the Nagasaki data?
What happened to it with it?
Well, yes, I mean, basically in this paper, they only show the Hiroshima data. And what happened to Nagasaki data? I mean, how come he doesn't show the Nagasaki data in all this? And I guess let me just make this point, and maybe we can have some conversation about this offline or something else. If you look at the data that Cutler and Welsh are showing, basically what it comes down to, the argument for hormesis comes down to the fact that in one zone particular, I think it's zone
Zone D.
Zone D. If you had, and you look, I mean, just consider the magnitude of this issue, which is after the bomb goes off and you have these different zones and you look at how many leukemia cases there are in each zone.
Well, for the survivors of those zones.
Yeah, for the survivors of this, and how chaotic that situation must be. And you look at this, and basically, in the paper here, the number of cases of leukemia in zone Z is 3. I'm sorry, is 3.
Zone D.
In zone D. So if you had, and I don't know, there's some error bars in this graph, which I don't know where the error bars come from, but let's put it this way. If you had 6 more cases in zone D, your whole hormesis effect would be gone. So 6 leukemia cases would eliminate completely the hormesis from this.
Zone D was 92 cases. Zone E
that's
was
the cases per million. So there's only 3 actual cases. There's only 3 actual cases. And then you normalized it to per million. So it's only 3 cases. So we can talk about this more offline if you don't mind, because I'm very intrigued by this. I would make one last comment too. This is like they published this paper in like a predatory journal. So I was just flabbergasted when I was looking at this last night. And what tipped me off to this is that the received date is December 22nd and the accepted date is December 28th. So in 6 days, they reviewed the paper. And I don't know how many people here have published papers, but I never heard of a case where you accept the paper in 6 days, and then, which made me suspicious right off the bat. And then I saw that this is published by the Omics Publishing Group. which was sued by the FTC like a number of years ago. So this is a predatory, what's called a predatory publisher.
How do you
So,
mean predatory? Can you define that?
you basically, there's no peer review. You pay to have it published, and then it's quoted around. That's what I mean by predatory. You pay
Okay.
them several $1,000s, and there's no peer review process. And I believe there's no peer review process because I never heard of a paper getting accepted in 6 days. So so that's why I was curious when I looked at this paper. The paper itself was strange to me. And then I looked up what the publisher was, and you can look them up on Wikipedia, and it tells you that this is a predatory.
Yeah, sure.
So
Yeah, maybe I'll talk to Ed Galbraith about that.
And let's put it this way. I don't have a bias about this. I'm learning this stuff.
Mm.
You know, I have no concept of whether LNT is correct or not, whether hormesis is correct or not. I'm basically learning it from you. And so I'm just sort of being the skeptic a little bit as to whether I mean, I'm leaning to the conclusion that LNT probably isn't right by looking a lot of the data, but I'm not convinced yet about hormesis, if that's based on the 2 pieces of data that are being shown. And
There's more in the LNT report, or hormesis is pretty well established. And Richard could talk more about that than I could, about the efficacy or the veracity of the hormesis concept as distinct from homeopathy, which is like unicorns and rainbows. But hormesis, a little bit of poison is good for you. Paracelsus, it's the dose that makes the poison. Stimulating and upregulating the body, similar to what a vaccine does. Richard, can you speak on that?
I think after 2 hours, many of our bladders are getting rather full. And
Well, go to the bathroom.
I suggest that we continue this conversation
All right.
on November the 4th. There's a
Okay.
lot of material there that we're ignoring, and I think it's way premature to be discussing it. So why don't we just carry on November the 4th? Okay?
Sounds good. All right.
Okay.
Thanks a lot. Yeah,
Thank you,
and
Mike.
Joseph, please send me that stuff. All right.
Yeah.
Sure, I will.
Okay.
Thank you. That's
Take
great.
care.
I appreciate, maybe we can have some more conversation offline. I would appreciate it.
Yeah. Yeah, sure. Yeah, send it over.
Great.
All right.
Thanks a lot.
Okay.
Thanks a lot, Richard.
Yeah. Bye-bye now. Thank you all
Okay,
for
bye-bye.
coming.
Bye-bye.
Yep.
Bye. Thank you.
Yep.
Thank you all again. Appreciate it.
Thank you.
You're quite welcome. I'm looking forward to it. I'll see you on the 4th.
Yes, indeed. Okay.
All right. Hey, and you got to run now, but yeah, I mean, I had some really good questions there, and I might have to do some revisions, but that's the way it goes. Yeah.
Oh, that's fine. That's what this is all about.
All right,
Is
man.
learning and sharing. So that's wonderful.
Speaking of
Thanks.
learning and sharing, Richard, are you going to share any of your personal concerns with your heart issue? That's a complicated disease you labeled in that email.
Yes. I wear these glasses because underneath I have some periorbital edema that goes along with the curious little compounds that are circulating in my body. But so that's another whole story. But I do appreciate everybody's input, and particularly your very, very wise remarks everybody's made today. So thank you all.
Yeah.
All right, man.
Good luck with your ongoing condition. That's a
Thank you so
complicated
much.
thing. The little I learned about it, it's like, whoa, that's one complicated thing. You leave it to Richard to get a tricky one. Okay, Richard, see you next week.
Okay. Thanks all.
Thank you.
Bye-bye.
Okay, bye-bye.